we talked about how energy goes through an ecosystem, starting with the sun, usually, and producers, consumers, and so on. What happens to matter? Well, we know that producers uptake matter from, say, the soil. Producers. This is from abiotic environment. Tick. And then consumers take up the mass or matter from the producers. Consumer. And another consumer. And so on. What happens though if the top consumer dies? Or any consumer dies, or any producer dies without being consumed? Well then, we've talked about how, you should have learned how, there are categories of consumers, such as herbivores, omnivores, and carnivores. Herbivores eat mainly producers. Carnivores eat mainly consumers. Omnivores are fine with both. Now we point out that even creatures you think of as herbivores actually do eat some consumers. For example, think of a deer that's going around eating shoots off of trees. Does it care to pluck the caterpillar off the leaf before it eats it? No, it just eats the caterpillar with the leaf. So, technically herbivore, carnivore, and omnivore are just general terms. Now what happens if any of these consumers or producers die? Well, their bodies decompose, right? So, or get scavenged by other consumers. What is this category of consumer called? Detritivore. So what do we think they eat? You may have heard of the term detritus as a reference to garbage. And detritus eventually gets degraded enough that it becomes considered part of the abiotic environment. So that's why here we say that this is a biogeochemical cycle. And here we note biotic and abiotic environment. This is not just a biochemical cycle. So, by biogeochemical cycles, the definition is the movement of matter through the biotic and abiotic environments. So, the water cycle is the most obvious, I would say. Why do we say it's the most obvious? Well, look up at the sky. There's probably clouds up there. Or it's raining. Or depending on where you are, there may not be any of these. But it's still pretty obvious when you see, say, rivers, lakes, and oceans. Here, we have transpiration from plants. We also have evaporation. Evaporation occurs also in plants and in bodies of water, but in plants, transpiration is much bigger than evaporation for the simple reason that plants have evolved to have waxy cuticles that keep the water in for the most part. Of course, sometimes they need to open up holes in the cuticle to let carbon dioxide in and oxygen out so that they can continue to photosynthesize. This is why we typically often find ourselves using the general term evapotranspiration. All right. What happens after it evaporates or transpirates? Well, the water gets blown with the wind. It rises. It cools down. And eventually, the amount of water vapor air can hold increases with the temperature. At 100 degrees Celsius, a gas can be pure water vapor and it will not condense because it's a boiling point of water. So if you cool it below that, then if it's purely water vapor, it'll start to condense. However, if you add some air, the water vapor can stay mixed in with the air and it will not condense. until you drop it below the maximum amount that the volume can hold under that temperature. So when you drop the temperature, you drop the maximum amount, and therefore once that goes under the amount that's actually there, the extra stuff just falls out pretty much. And that's why we have condensation. Alright, what happens when it comes down? When it falls out, so to speak? Well, first, initially, it does nothing. It stays up there. The clouds that you see are little suspended water particles. And I mean particles not in terms of molecules, but little water droplets. So what happens when these droplets grow big enough? Well, they fall down. Fall out of the cloud and to the ground. Sometimes they don't make it to the ground, but we're not counting that. So what happens here? Precipitation. This may be in the form of rain, snow, or hail, or whatever. So what happens once it hits the ground? Well, it can enter the ground. We call this infiltration. So think about rocks. Say we have a crack in a rock, and we have other cracks radiating off of this and mixing with other cracks somewhere in the rock. This is due to year after year of, for example, weathering or mechanical stress or ice. When ice freezes, it expands, which makes these cracks bigger. So these are forms of weathering. And the water falls here, and it goes straight in. And then it leaches out into the rock. What else can happen? Well, if it falls on soil or sand, they are basically little particles that are all packed fairly closely together, but hey, wait, there's lots of space, which means it just goes straight in and through. Now, if it falls on an impermeable surface, which it cannot permeate, i.e. go through, it will run off, right? That's why we call this runoff. So rivers are basically really big runoff streams. Now, why do lakes form? Well, it's possible that the ground under them is not permeable to water, and it just happens to be a depression, which means the water just accumulates there. Alternatively, it might be that the ground is permeable, but it's not permeable enough. So relatively impermeable, and the water coming in is just too much, so it fills up. And there's also the option that the local water table, i.e. the level of underground water, is just high enough that this depression happens to be low enough to let the groundwater seep into the lake, instead of the other way around. But these dynamics are for later science classes. So they're too complicated for now. Also, what happens when the water goes through the rocks? They go under the surface, and we call this subsurface flow. Subsurface flow is more significant than surface flow. There's more water being carried through it. So, let's think about the next big thing of life. We know that life on Earth is based on water, and it's based on carbon. So, let's talk about carbon. The carbon cycle has a lot more chemical changes. Water, yes, okay, there's photosynthesis, which uses water, and there's respiration that makes water, but for the most part, water tends to pass through biological systems unchanged. In the carbon cycle, on the other hand, it's quite different. So here, we have producers, we have consumers, and we have decomposers. Here we again have producers, and then consumers, and so on. So, P. Producer. C. Consumer. D. Decomposer. So all of these will respire. So all of them have respiration. Respiration. And here we have photosynthesis and other methods of uptake. For example, when carbon dioxide enters water, it forms carbonic acid. This carbonic acid can be used to extract carbonate, which is used by marine organisms to build their shells. So let's just label this as uptake in general. What happens here? This is the sediment. And when the sediment gets compacted over long periods of time, compaction, we get fossil fuels. And then here is combustion. I won't do the uptake respiration labeling for the terrestrial ecosystem. However, regardless, here we still have detritus. So here we have overall atmospheric, CO2. We know that combustion feeds into it, we know respiration feeds into it, and uptake takes away. To be perfectly clear, this uptake is supposed to go here, but it's a little small. And also my writing is in white. Okay. So, we should point out that to humans, the most valuable carbon deposits are fossil fuels. For example, coal. Let's think about coal for a moment. Well, it began with ancient swamps or peat bogs, and then over long periods of time and great pressure, eventually all the volatile compounds are driven off, and we end up left with essentially carbon. So coal comes in various forms. For example, peat can be considered a primitive form of coal. Lignite, typically somewhere around 70% carbon. And then we have bituminous coal. And this is somewhere around, 85%-ish. And then we have anthracite. Anthracite is the highest grade of coal. It has been compressed for the longest time, and it is the purest, at somewhere in the neighborhood of 95% carbon. Hydrocarbons, such as petroleum, are, well, rather less carbon than this. So, why are they less carbon? Well, let's think about what a hydrocarbon means. Hydrocarbons are CH, H, repeated n times, with an H at either end. Let's think about this repeating unit. Carbon has an atomic mass of 12. Hydrogen is 1, more or less. So, 2 to 12. 12 out of 14 is not nearly as much as 19 out of 20. Alright, so even though we've just figured out that oil and methane gas, for that matter, which is just N equals 1, methane is the most common gas, by the way. Gas and oil tend to occur together for the simple reason that when you have conditions that are right for the formation of hydrocarbons, you form both long and short chains. What happens to the short chains? They exist in gas form. Now we do point out that oil and gas deposits are embedded in stones, permeable stones. They are not just big pools of oil under the ground, covered by a big bubble of gas. So, even though we know that coal can contain more carbon per mass, it is petroleum that is usually considered the most worrying. Why? Because we use more of it. At least more of it in obvious ways that can potentially be cut down on. Coal, for the most part, gets used in industry where it's unavoidable. Like we can't avoid using carbon for industry. For example, coking for making steel. The so-called coke that's used for making steel is coal. This is not an avoidable expense. However, we could avoid using coal to power our many power generators, true, but the most obvious sign of use of fossil fuels is, well, other than the fact that you probably have a gas water heater in your home if you live in North America, the fact that you probably have a car, or at least can see cars fairly often, or other internal combustion engines. They typically run on petroleum. So there are places where they run on synthetic gas and such, but for the most part they run on petroleum, so that's the most conspicuous, and it also should be the easiest to cut down on for the simple reason that a human with a bicycle can outrace any creature on Earth in terms of endurance, in theory. Yes, I do realize that albatrosses stay flying year-round and they don't come down, but that's with the use of thermal upwellings and such. If there was no wind and the air was stationary, a human on a bicycle is said to be able to outlast an albatross or other bird trying to stay afloat. That's because humans have a very good heat regulation system, or rather cooling system technically, not heating. So, the takeaway, if you really want to help keep the carbon cycle fairly natural, go for a bicycle. We've already managed to avoid an ice age, so a bicycle now would be a good idea to avoid overdoing it. Why do I say we've avoided an ice age? It's because the little ice age from the late 1400s to the 1500s, before the Industrial Revolution, that was no joke. If we hadn't had the Industrial Revolution, most likely we would have had another ice age, which would have been devastating for human civilization. So nitrogen. Wait, whoa. Why are we talking about nitrogen cycling? Isn't it 78% of the atmosphere? Well, yes, but nitrogen exists in diatomic form. This triple bond is extremely strong. It is so strong that most organisms cannot break it. So if they cannot break this triple bond, they can't use the nitrogen to build proteins, right? This is why nitrifying bacteria evolved. So here we have nitrifying bacteria. They are capable of fixing atmospheric nitrogen, Why is this such an advantage that they managed to evolve, despite the fact that it costs so much energy to fix nitrogen? It's because when you are able to supply your own nitrogen, you aren't dependent on others to provide you with the building blocks of your proteins nearly as much as, say, legumes are. Legume plants, including beans, legumes, they emit chemical compounds into the soil, and they attract rhizopus bacteria, which are capable of colonizing their roots, inducing the plant to form root nodules, and then the legume takes nitrogen from the bacteria and it provides them with sugars and other compounds they need to survive, such as water and minerals. So, what happens when these nitrifying bacteria and legumes and all that stuff manage to fix the nitrogen, including using lightning bolts to force nitrogen and oxygen to combine? Well, when they manage to fix nitrogen, eventually you end up with stuff in soil. What stuff? Nitrates, nitrite, and ammonia. The name ammonia actually came from sal ammoniac, which was salt of Ammon, because it happened to be mined near a temple to Ammon, an Egyptian god. So, what happens here? Well, we see that it's uptaken by photosynthesizers, so we label this as uptake. And producers, and here it gets consumed by consumers. Alright, which may get consumed by other consumers. Eventually though, the consumers die, or the producers who didn't get consumed die, and the soil regains its nitrogen content by decomposition. However, you would think, hey, why is the atmosphere still 78% nitrogen? N2 gas, up here. We should label this. Why is, we should also label rhizopus, because it is a very important genus of bacteria as far as farmers are concerned. So, why do we have any nitrogen left in the atmosphere? Well, clearly, somebody has to be the opposite of the nitrifying bacteria. Why? Think about this for a moment. Hey, there are all these nitrogen compounds here. If I can turn them into nitrogen gas, I can release a lot of energy I can use. Well, that's basically how denitrifying bacteria evolved. Their ancestors managed to spontaneously gain the mutation needed to recombine nitrogen compounds into nitrogen gas. And this was successful. This was a successful strategy. They survived. They've continued to reproduce. The lineage has survived. Denitrifying bacteria. Now, the nitrogen cycle is, of course, not entirely terrestrial. It also occurs in the oceans. Otherwise, you wouldn't be able to eat fish, which are very rich in proteins, and proteins are rich in nitrogen. So, even though nitrogen is considered often a limiting nutrient, it is, of course, not fully terrestrial. That's why the marine organisms have nitrogen in them. Now, marine organisms tend to be rich in phosphorus too, such as, say, kelp. Various types of kelp can be used to treat phosphorus deficiency. Why is this? Well, Phosphorus exists as phosphate ion. It is negative, like nitrate and nitrite ions. So the reason farmers tend to prefer using ammonia when they fertilize their fields. Why? Because soil particles are mostly silicate. Silica tends to be negative at the surface. So as you have probably learned before from magnets or from various TV shows about electromagnetism in general, negative charges repulse each other. Positive charges, such as ammonia, will be attracted. So what happens next? Well, when it rains, the negative ions tend to flow away, whereas the positive charges stick to the rocks. Plants get the positive charges unstuck from the rocks by exchanging protons from them, but that's another story for biology class later. The point is that phosphate ions are quite soluble in water, which means that much of the cycle occurs in the sea. So suppose here we have the sea, and we have some mountains up here. And it rains on these mountains. Cloud. Rain. Or snow, for that matter. So these mountains have some sedimentary rocks in them. Sedimentary rocks formed on the ocean floor, alright? So what happens? Or even phosphate-containing igneous rocks will work, because think about subduction zones where the seafloor plunges under a continental plate and melts, and then volcanoes happen. That means that the magma has to contain some phosphate. It doesn't get destroyed. So, regardless, phosphate-containing rocks eventually start losing their phosphate content once they get rained on enough times. And when this happens, the phosphate goes with the water to the sea. Of course, in between, they might go to producers, or even consumers directly, depending on the creature. Producers, etc. But they eventually rejoin the stream and proceed to the sea. In the sea, of course, they can also go producers, etc. So here we have dissolved phosphate. PO4 minus. Some of this becomes trapped in the detritus. We point out that some of this happens too. So they go into the sediment. Why do we call sedimentary rocks sedimentary? Because they begin as sediment. So the sediment compacts over geologic time, and then it either gets upthrust by two oceanic plates crashing together, or it gets subducted and comes up again as an igneous rock that contains phosphate, or alternatively, it simply undergoes seafloor uplift, which results in phosphate-containing sedimentary rocks above sea level. Lo and behold, what are these mountains? Essentially, that's exactly what they are. Alright. So, in summary, matter is cycled through ecosystems by biogeochemical cycles. Now, water, for the most part, stays water as it passes through various organisms. It occurs in all states, liquid, solid, and gas in nature, and as it moves through the water cycle. To call the solid moving through the water cycle is a little bit of a misnomer for the simple reason that until it melts, it mostly stays where it fell. Right? Think about it. So carbon moves through between the abiotic and biotic elements of the cycle. Well, elements is probably not the right term given carbon is an element. Components, better. So by photosynthesis and cellular respiration. It is true that water also changes through these two, but for the most part water stays the same. Nitrogen, well, it is removed from the atmosphere by microorganisms, nitrifying bacteria, and it is returned to the atmosphere by denitrifying bacteria. In between, it cycles between producers, consumers, and decomposers. So, nitrogen exists in a few main forms. Well, okay, obviously there is atmospheric nitrogen, which is N2 gas. And it also exists as nitrate, NO3 minus, nitrite, which is NO2 minus, and as NH4 plus, ammonia. Well, technically this is ammonium. This is the charged form of ammonia. Ammonia is technically NH3, but we represent it as NH4 plus because in nature that is the dominant form. Alright, so manufacturing nitrogen compounds takes lots of energy. So most nitrogen fixers have either specialized cells or symbiosis to sustain their nitrogen fixing activities, or alternatively their environments are simply nitrogen poor enough that to evolve this trait is more than worthwhile. And what else? Let's think about this for a second. Why is it then that given these are so expensive to make in terms of energy, why would we want to send these back to dinitrogen? It's because dinitrogen is very high in energy. This bond here is very high in energy. That makes the compound itself technically very low in energy, but that's pretty much semantics and a matter of concept. So, this bond is very high in energy. Forming it releases lots of energy. So that's a way of life, right? You can get energy from this. Life needs energy to live. Hence the evolution of denitrifying bacteria. For the most part, we consider carbon, oxygen, and hydrogen to be readily available to living organisms. Of course, this is for the most part. There are many exceptions. For example, there are many environments where there is little or no oxygen, say in the swamp mud, in pretty much any swamp. Or alternatively, at the bottom of a stratified lake. Consider the fact that water is densest at 4 degrees Celsius. During the winter, if a lake freezes, what is the temperature is it at the top? 0 Celsius. Or, okay, I admit the ice may be colder, but the boundary between ice and water is going to be 0 degrees Celsius. Or thereabouts, depending on salt content. So, what happens when it warms up in spring? The ice melts, the spring winds turn over the water. Well, what happens in summer when the lake is getting lots of sun? The top layer heats up. The bottom does not. So the warm water pretty much stays on top of the cold water with a thermocline. So warm, thermocline, cold. Alright. Some of the light penetrates into the thermocline, just saying. So, what happens here? Well, the bottom is not getting any new oxygen from the air. So if there's lots of stuff decomposing down there, it soon uses up all the oxygen, and thus nothing that requires oxygen can live down here. So this is a little bit conditional. Hydrogen, on the other hand, is typically not considered very conditional. Human activities disrupt biogeochemical cycles. Okay, sounds pretty obvious, right? We've just talked about earlier the combustion of fossil fuels. That's a big disruption compared to the typical biogeochemical cycle. This is not to say disrupting it is not a good thing. The Little Ice Age would have been an actual ice age if not for the Industrial Revolution. However, too much of a good thing or too much of a not bad thing can be a bad thing, right? So we should take care to reduce our disruption of biogeochemical cycles as much as possible and as quickly as possible. And this is actually also healthy for us to reduce. Why? I mean, other than the fact that, oh, less extreme weather events, cooler summers, we don't need to worry so much about heat stroke. The other reason is the fact that the most obvious and easy to reduce part, well, one of the most easy to reduce parts, includes riding a bicycle. It is healthy for you. So, other than these semantics, that's it for this section. See you later.